Welcome to The Explainer. Today, we are looking at a truly massive breakthrough in the world of artificial intelligence coming from DeepSeek. We're talking about an advancement that gives AI an incredible, entirely new way to actually see and locate objects within images. For a long time, we've thought of computer vision as basically just crunching pixels, right? But this new approach, it completely flips the script. We are moving away from those poetic, convoluted text descriptions and stepping into a future where the AI, well, it simply points. Okay, let's dive into this. If you ask a standard AI model, like one from the previous generation, to count the number of people in a crowded photograph, the way it processes that request is honestly pretty clunky. It tries to use words. It'll think something like, okay, well, there are people on the upper left, and then a bunch of stripy guys in 2 rows. Wait, maybe that's kind of 3 rows. Some are standing, some are sitting. It gets completely lost in the weeds. It is so confusing to try and count things up using only words. It's highly prone to error, and it forces the system to burn through massive amounts of compute time just trying to verbally describe the visual space. But look at DeepSeek's method. Think about what we humans would do in that exact situation. We wouldn't describe the scene, we'd just take our index finger and physically point at the image. 1, 2, 3, and so on. And that is exactly what this new technique does. It introduces visual primitives. It literally allows the AI system to point at things while it's thinking, rather than trying to act like a poet describing a painting. And the efficiency gains from this simple shift, they're absolutely staggering. Because this intuitive pointing method is so much more direct, it actually requires 90% fewer visual tokens than most frontier models out there. To put that into perspective, that means 90% less data to process the exact same image. In an industry where specialized hardware and processing tokens cost an absolute fortune, having a system that dramatically cuts down the visual noise is just fantastic. Less is actually more here. It's delivering results faster, it's significantly cheaper to run, and it's fundamentally more accurate. Moving right along to Section 1, Beyond Describing, the Power of Visual Primitives. Thinking with these visual primitives unlocks entirely new capabilities that go way beyond just counting objects. The core takeaway here is simple. Don't describe images like a poet. Point like a human. When the AI is allowed to point, it gains this wild ability to perform complex topological reasoning. Imagine giving the AI a picture of a really complex maze with a start and an end point. Previously, an AI might just try to guess the solution. But with visual primitives, it doesn't just give you the answer. It literally traces the path visually. You can actually watch its entire thought process unfold. Or imagine a messy, detailed drawing where you ask the AI, hey, where does the crown connect to the octopus? It answers correctly, but more importantly, you can trace exactly how it came to that specific conclusion. This is huge for transparency. If something goes wrong or the AI hallucinates, researchers can just go in, find the exact mistake in the visual trace, and fix it. It puts us one massive step closer to AI systems we can actually understand. So, how does it stack up? Well, this free system matches or outright beats almost everything out there, going toe-to-toe with closed billion-dollar frontier systems. And what you really need to take away here is how rigorously these results were verified. The researchers averaged their performance across 7 totally independent benchmarks. Crucially, they completely excluded all of their own in-house benchmarks. This is a big deal in the research community because, the oldest trick in the book for gaming the system is to just invent a new benchmark that perfectly fits your model's unique quirks. By relying entirely on independent tests, DeepSeek proved this isn't some fluke. It's a genuine leap forward in visual processing. Now, what's really interesting about this next concept is how they pulled it off. Section 2, the magic trick revealed. On-policy distillation. To understand how they built this highly efficient model, we have to look at the mechanics under the hood. The entire framework relies on a concept called on-policy distillation. Now, for those seeking a direct understanding, on-policy distillation is basically a training method where a single versatile student model learns to mimic the behaviors of multiple highly specialized expert teacher models. Instead of trying to build one giant brain from scratch that knows absolutely everything, you start with narrow experts and distill their specific knowledge down into one unified system. Think of it kind of like a highly specialized school. Imagine one of these expert teacher models is the absolute world champion at drawing bounding boxes. Literally, nobody does boxes better. Another teacher model is exclusively an expert at tracing mazes with points. But out in the real world, we don't want a fragmented system where we have to ask 10 different models to look at one picture, right? We want the versatile student. We want one cohesive AI that can seamlessly integrate all of these distinct visual thinking methods into a single, easy-to-use package. To bridge that gap, they use this continuous three-step learning loop. Step 1, the student model is given a visual task, and it makes an attempt, effectively saying, okay, here is what I would try to do. Step 2, the expert teacher steps in, evaluates the attempt, and demonstrates the correct approach, essentially saying, well, that's close, but here is what I would have done. And finally, step 3, the student adjusts its internal parameters and fully internalizes that specific skill. By looping through this exact distillation process millions of times across all sorts of specialized tasks, the student model perfectly absorbs the collective intelligence of all its teachers. Which brings us to Section 3, the open weight advantage. Free blueprints for the community.
Looking at the macro-level impact, this research acts as a free blueprint for the entire community. As noted in our sources, it's going to become more and more crucial to own your own AI systems with free, open weights models. This research paper doesn't actually have a proprietary, lockdown model attached to it. It describes the concept of this visual pointing technique in exhaustive detail for anyone to use. As we observe the current landscape of AI, we're seeing large, well-known AI companies heading towards initial public offerings. And as they transition into publicly traded ventures, their fundamental drive will naturally be to maximize profits every single quarter. By neutrally contrasting that trend against this free, open source approach, we see the true value here. This pointing technique can potentially be added to many existing free models, democratizing this high-level intelligence for everyone, rather than keeping it locked away behind an expensive corporate paywall.
So, the crucial point is, we need to look at the whole picture. Section 4, the reality check. Technical limitations and hurdles. While this is undeniably an incredible tool, we need to bring the excitement back down to earth for a second and examine the very real flaws of this system from an expert research viewpoint. First off, the AI doesn't just wake up and automatically start doing this highly efficient pointing. It actually still requires specific text words as a prompt cue to trigger this kind of thinking. Second, remember how we praised it for using 90% fewer tokens? Well, a byproduct of that lower resolution is that it severely struggles with thin structures. Counting people or drawing bounding boxes? Totally fine. But if you ask it to identify individual blades of grass or tiny strands of hair, the lack of high-resolution pixels causes it to fail. And third, this topological reasoning has limited generalization. If you train it on mazes and octopuses, it's brilliant. But if you throw a completely alien, never-before-seen topology at it, it just may not be robust enough to adopt yet. It's incredibly important to look past the media hype and recognize that AI development is an ongoing hurdle of trial and error. Which leaves us looking toward the future. Based on everything we've unpacked today, here is a final thought to consider. Will open-weight blueprints, like the distillation methods we just explored, or closed, billion-dollar systems, ultimately define the next era of AI? The architecture of tomorrow's intelligence is literally being written right now. Thank you so much for joining me on this explainer. I hope you found this breakdown incredibly helpful, and I absolutely can't wait to dive into our next topic with you.